Okay, I'll spend 2 weeks for the topic of econometric, economic forecasting. Okay, and in fact, I'm going to introduce the 3 ways, which maybe is the most popular ways to do the forecasting. Okay, in business, in business area. Okay, and let me say something about this economic forecasting. Usually is useful in what area in business. Okay, the first one is planning and control. Maybe something like inventory management, production planning, or sales management, something like that. Okay, and or in marketing. Okay, in marketing to forecast the response of the sales. Okay, in different market schemes. Okay, or we may forecast. This is most by government. Okay, they want to forecast those key economic variables such as GDP, unemployment rate, consumption, investment, interest rate, something like this one. Okay, or we do it in financial assets management, which is like the topic we just discussed last week about assets return volatility. So we can do that for forecasting too. Okay, or those government budgeting, or maybe the governments also like to forecast the fertility or mortality rates. Okay, and there may be something like crisis management, currency devaluation, and so forth and so on. Okay, all right. So it means that it's useful. Okay, and actually, by learning regression analysis, not really a regression analysis, is econometric. The topic of econometrics, usually there are 3 uses. One is called, you want to know this basic statistics, summary statistics. Okay, then we can know some basic statistics properties, something like mean, variance, or many kind of this. So that is what we call summary statistics. And the second one is what we cover most of the time. We spend most of the time in this class and the one last semester, which we call research methods. And this is more focus on hypothesis testing. Okay, so this is the second use of a hypothesis testing, usually in business area. Okay, you are working with cross-sectional data. Usually we like to know the relationship between X and Y. Okay, so most of the situation we focus on the hypothesis testing. So hypothesis testing in business area is very important. I'm not sure about this engineering departments. Okay, and the third one is forecasting. And usually the forecasting is more focused on time series data. Okay, it's not cross-sectional data. It's time series data. Okay, so therefore, to learn how to do the forecasting is also very important topic. Okay, and what's the difference between let me show this way. There are 3 ways. Okay, there's 3 ways. Actually, there are many ways, but we're considering more focus on 3 ways. One is using regression models. The second one is using autoregressive integrated moving average. I think if you heard about this ARIMA before, then we're going to talk about ARIMA today too. Okay, and this is ARIMA usually popularized by, we call them Box-Jenkins methodology. Okay, and the third one I'm going to talk about is vector auto regression, which is VAR. Okay, I'm going to leave this one next semester and more focus on the second one, and just briefly say something about regression models, okay, because we learn a lot in regression models. Okay, and this is the three ways, three methodologies. Okay, one is by today focus on Box-Jenkins methodology, and the second next week is VAR. Okay, so first of all, for using these regression models, and we know that the forecasting probably the most important purpose for the regression models if you're using time series data. Okay, and so for example, we just used this remember we just used this example last week for is last week or sometimes 2 or 3 weeks ago about PCE and PDI. PCE is the per capita personal consumption, and PDI is the personal disposal income. Okay, and in economics, the equation 1 is important, and usually the beta 1 is called consumption propensity. Okay, so we call it marginal propensity to the consumers. Okay, since C is the consumption, DI, PCE is consumption, PDI is the disposal income. Okay, and so this is basic in economics. Okay, so I like all of you. Do you have all this data? I think I put it in the iLearnings, our class systems. I need to, okay, why don't you just download this 2 data set first. This morning I'm going to use this one. The other one is called IBM data. Okay, so go to the iLearnings and download this 2 data set first. Okay, let me see the data. This is well, actually, PCE and PDI data is a seasonal data. This is 156 divided by 4, which is how many? 34 divided by 4, 39 seasons. Okay, so which is let me see the data. Yeah, this is all the data. Okay, I think it's in $1 billion. Okay. Okay, and this one. Okay. And after you download the data, then you may like to just run the regression of equation 1, and you will have the output. This is a chart, okay? and this is the output by using OLS. Okay, and this one is what we call propensity. So it means that the 1 billion's income increase will lead to consumption, the increase of consumption by 0.95 billion dollars. Okay, all right. So this is pretty high, right? Okay, means most of the income will be consumed by the consumers. Okay, then you see this one, right? What do you see from this chart? And if we do the regression analysis, then what do you see from this output? Since we wanted, if I wanted to use this regression analysis as a forecasting model, so I need to be, the model should be, well developed. Okay, then all the numbers, or is there's no problem with this model. With this model, what did you see? Did you find anything which you need to do some correction in order to do the forecasting? Did you see anything which you need to do something in order to use as a forecasting model? If you do this output. Or this is just a perfect model? Usually the output tell us something about the data, right? The information about the data. And this is what we all learn the whole semester, whole year. Okay, did you see this one? Durbin-Watson statistics. What does that mean? Durbin-Watson statistics. Usually, what do we like to see the Durbin-Watson statistics? Around 2. Okay, so this is too small, right? It's pretty small. It means that positive zero correlations, right? Right? So actually, if we see that, and we need to do something about the autocorrelation. So maybe we can run, run something like this one. Well, I'll say some terms before we really do the forecasting. Okay, and that's correct this model later on. Okay, let me introduce some terms which is confusing. Sometimes it's confusing in forecasting topic. Okay. For forecast, we do have point forecast and interval forecasting. Okay. Do you know what's the difference between the point forecasting and interval forecasting? Let's see, where is the, okay, here. There's no ink at all. This is no ink either. But this one, maybe this one. I'm just using simple, okay? Usually, this is the estimate. So this is y hat equal to beta 0 hat, beta 1 hat x. Okay? So point estimate means if you use any one value of x, then plug into this equation. Since beta 0 hat and beta 1 hat is already known, we estimate it, right? So given the x, then you will know the y hat. This is what we call point estimate. But remember, the regression. In the regression analysis, we need to really pay attention to the range of the x. What do you mean by range of the x? Means the original data set with the smallest value of the x and the largest value of the x. Okay? In other words, all this regression analysis, this equation is based on those values to do the relationship, to estimate the relationship between x and y. So if we have the x value, which is our range of the original x range, then this equation may not, the relationship of this equation may not exist. So I can use in one example. If I'm forecast the height, F-I-G-E-I-G-H-T. So if I say y is the height and x is the age. Okay? The age and what kind of relationship of the age and the height? Now we really have two growth periods, right? For the babies, when they were born up to maybe 3 years old, they grow faster, right? And the other periods is when you are, in young age, maybe something like 10 to 15, or 12 to 15, which is the period which grow faster. Okay, so age x. If we focus on these two age, then the relationship between x and y cannot be applied to the age after maybe like after 40 years old. Do you still grow after 40 years old? No, we don't grow, right? We don't grow taller, right? Okay? So that will not be applied to the age beyond which you forecasted. Okay? So if you do that, then the model cannot be used to do the forecasting because the error is so huge. Okay? All right? So point forecast is you plug all these numbers in, then you will have the forecast of the y hat. And what is interval forecasting? Okay, we have some kind of formulas which not very familiar with, but never mind. If we do the computers work for us. They will calculate it, and which we call it confidence interval. So actually something like pretty close to something like this one. So this is an interval. There's some certain value of this one if it's x0, okay? then we have the forecasting is y hat. But confidence interval forecasting is this range. So it will provide the numbers within these two numbers. So we call it interval. Okay? And this is forecast the expected value of the y hat. Okay? So so we need to know that whether we're doing point forecast or interval forecast. So point forecast is just provide a single values, and interval forecast will be a range. It's an interval, just something like the chart. I just put it on the whiteboard. Okay, so we need to know that whether we want to do the point forecast or interval forecasting. Okay, and the second one is called ex post forecast or ex ante forecast. So what do we mean by ex post or ex ante forecast? Let me show you some definitions. Maybe you'll see it clearly. Okay. In the ex post forecast periods, we also know the values of regressant or regressors. So maybe if I have the data set, which is something like 40 years old, 40 years data, annual data, but actually I have more than 40, maybe I have 45. So I leave the 5 years as a whole periods. So I'll do the forecasting, I'll do the estimation based on the 40 years and leave the 5 years to evaluate how good of my regression model. So if I do ex post, means that after I estimate the models, then I'm using already known regressor and regressant to assess, to evaluate how good my model, the forecasting of my model. This is called ex post. So you do know the regressant and also regressor. So this is X variable, this is Y variable. So usually we'll do that. I'll collect, just like the example I show. I have 45 samples, but I use the 40 years data to do the estimation and leave the 5 years to evaluate how good my model is. So this is called ex post forecast. And there's another one, it's called ex ante forecast. Means that I don't have any regressant and regressors. So maybe I just have those 45 years old annual data. Then I do all this 45 years data. Then after that, I don't have any regressors and regressant. The value of regressor, regressant. So I need to do the forecast of the regressor and the regressant in order to do the forecasting of by using this model. This is called ex ante. So you need to know that what kind of forecasting you are working with. And nowadays, I'm just working of ex post forecast. Means that I do have the data. So I leave some of the data as in holdover periods, and using that to estimate, assess how good, okay, my model is. Okay, the other terms is called conditional or unconditional forecast. So usually, for the regression analysis, we base on the value of X. So usually I have something to base on. So means I conditional on the X values. So usually we're doing conditional forecasting. Okay, And for unconditional forecast, there's more advanced methodology, which we didn't do it here. Okay, so you need to identify the three terms. One is point forecast or interval forecast, or either ex post or ex ante forecast, and conditional and unconditional. Okay, so we're doing conditional forecasting, we're using ex post forecasting, and we can do point or interval forecast. Okay, and the one we just show that using the PCE and PDI, if I consider the first order autocorrelations, this is what we do in EViews, right? You can put another one, it's called AR1, then you have this new models. Okay, what's the difference between these two? So my first, this is my, this is the one without consider first order autocorrelation. So this is 95, 0.95. But if I consider the autocorrelations, it turned out to be 0.975. Okay, so I'm bet this one, since I do see the problem with autocorrelations, and I do the corrections, and I think this one is much better than the second one, the one without consider that. So this is the regression analysis, using regression model to do the forecasting. And I think we spent the whole year to study the regression models, and we all bump into many situations. So after you have to correct all these problems, which we have in our regression model, and if this is the best one, then we just use this one to do the forecasting. So this is one way, one methodology, which is using regression model to do the forecasting. Okay, so I think this is nothing new. We just review it. But this model should be after you correct, is a correctly specified model to do the forecasting. Okay. All right, then the second one, I think we need to address a little bit more, is the second methodology, which is the focus of today. We call it Box-Jenkins methodology. Okay, usually we call it ARIMA models. Okay, and I'm going to introduce what's the difference between Box-Jenkins methodology, is what we call this ARIMA model, and the regression model. What's the difference of them? Anybody knows? Usually in the regression model, we always have X variables, right? So we will list it by the theory that we may have some certain X variables. So given or conditional on these X variables, then what is the Y? So this is what we call regression analysis. Okay, then Box-Jenkins called ARIMA model is just only use Y and the past information of the Y as well as the error terms of the Y. Okay, so something like this one. So the first one is called autoregressive model. The autoregressive model is just using YT, the previous Y. So they use themselves to explain everything. Okay, so YT and all the X is the lag of the Y. Okay, this is what we call autoregressive model. So we will say that this is dependent variable. This is the lag of dependent variable as an X variable. Okay, this is what we call the AR model. And if you have the lag up to P, then usually this is the notation. Say ARP. P is the lag of the model. And how do we determine the P? There's a lot of try and errors. And after you do the try and error, you can use the archaic information criteria or Schwartz information criteria. Usually we call it AIC or SIC. Okay, using these two informations to determine the lag. Okay, and now what's the moving average model? Moving average model is using YT, and this is the U. It's the arrow terms. Okay, use the current arrow term and the past periods arrow terms. So again, the Q is what we call MAQ model, and the Q is also decided, by try and error or empirical. And remember that, when we do the forecasting, even we do the regression models, we didn't really say something about it. But after we learn this time series data, we know that even we do the regression analysis, we need all these X variables and Y variables are stationary, right? And if they don't have they're not they're not stationary, but if their residuals is stationary, that'll be fine too, right? This is what we learned in the previous weeks, right? And and we call this co-integration, right? So if we do this models, and if the X and Y variables are not stationary, and we can check either X and Y by uniroots analysis test to see whether they are stationary. So if they are not stationary, then usually we take the difference of the original X or Y variables. And most of the time, in business, I'm not sure about in engineering. In business, after we take the difference, and it becomes stationary. Okay, so that turned out to be, okay. Well, I need to say this one first before I do the integration, integrated. Okay, and if I put AR and MR together, okay, these two models, I put them together, means what? Means I do have, I don't have that model. Okay, I will have the past of the YT as well as the arrow terms. Okay, then we call it ARMA model. Okay, I put these two together. And if those X and Y variables are not stationary, I can do the first difference of it, of the Y. Okay, in order to put it, then I will say this is ARIMA. So look at this one, ARMA. ARIMA means PDQ. The D is, I use the difference. If I use the first difference, I just difference once, is first difference, then D equal to 1. Usually in business area, and D equal to 1 will be the variables become stationary. Okay, so we'll call this ARIMA PDQ. Then P is the period of the original Y, and Q is the lag terms of the residual error terms. Then D is how many difference they do. Okay, and usually the P and Q actually is a lot of try and error. Okay, and the this Bach-Jensen methodology usually follow using 5 steps procedures. Okay, first of all, you need to do the identification, means you determine P, D, and Q. How do we do that? By looking at the parallelogram or partial parallelogram. Later on, I'm going to use another example, then let's do together for all these procedures, okay? The second one is after you have the models, then you do the estimation, okay? And sometimes you're using OLS, the other one, sometimes maybe other more high-tech estimation, but actually, computers work for us. Then checking, diagnostic checking with this ARIMAs, okay? And then you can do the forecasting. Okay, so we'll spend the rest of the time working with one example, which is IBM. So you all have that data? Okay, and okay, let's see the data first, okay, for the IBM. I have this one here. Usually it's easier to see using Excel file. It didn't turn on. This is an Excel file. Huh? How come it? Can I turn it on in Excel? Okay, I like to turn on in Excel. So this is from 2000, the first day of the 2000 up to if you see all this data, okay. In fact, there's not that many. Actually, the data is 687. Okay, so this is from 2000, January the 3rd to the 2002, in August the 20th. So this is the daily data, okay? And let's see this one, okay? This is the closing price of the IBM, closing price, okay? Price, stock price, okay? And we talked about this one last week, that usually in economics, those kind of either return, or we like to know the return, right? So usually we're taking the log of it, natural log of it, of the original data. So this one is the one is already take the natural log of the closing price. Okay, and we work on the log one, okay, the log data. And this is what we have in IBM. Okay, so let's see. So what do we do? By following the 4 steps. The first one is what? What do we do if we do follow this step 4? The step 1, we need to identification this, what kind of model is this, right? And how do we do that? We check the parallelograms and partial parallelograms. So would you do that? Would you please do that? Using eViews. How do you do that? Remember that? Well, we need to use the, what do we do for the, okay, first of all, we need to check whether they're stationary or not, right? So check it first. Check the stationary, whether it is stationary or not. Let's see. How do you do the are they stationary? Log, right? Open it. View. Unit root test. Okay. Maybe I'll just use, if I don't see any daily, so I put a 0. So do not reject null hypothesis. Maybe put it 4 or see whether it is. This is okay. This do not reject null hypothesis, right? So if I using original log of it, it is non-stationary, right? So how about I take the first log, first difference of it. So let me take the first difference. Where is it? What should I do? I just close it, so I need to do it again. Okay, so I'll generate and so using this one and open it, view parallelogram, then this one. Okay, this is what I do for the how many? 36? Well, maybe put it 40. On parallelogram, legs up to 40, maybe. Just try it. Okay, what did you see from this parallelogram? Well, I have the parallelogram and the partial parallelogram. What did you see from here? What did you see from here? It's not very clearly, right? But there's another way, okay? Since this is the correlation coefficient, okay, all this number is correlation coefficient, okay, we can set up the confidence interval of the correlation coefficient to test whether this correlation coefficient is within the confidence interval. If it is within confidence interval, then we can see that those is not within the confidence interval. Okay, means that the correlation coefficient is too big, outside the range of confidence interval. So how do we do this confidence interval? I can use the sample size. Okay, it's right on here. So this is the since we're working with the correlation coefficient, so which is we see this 0. I mean the hypothesis of correlation coefficient is 0. Okay, plus and minus we can use the sample size. Okay, so here I do have the sample size 687. So why don't you calculate this one? It's 0 plus or minus. What is the number of this? 0. What? Can you calculate this for me? Zero, 3, 8, something like this one. Okay? Huh? Take the square root of it. Take the square root. Did you take the square root of it? Okay, okay. So this is right? Oh, I'm sorry. We need to times the, t, take the square root of it, which is something like, this is huge sample size. This is confidence interval. Remember that we need to, I'm sorry. Oh. 687. Oh, this is, all right, but there's not big difference. Oh, okay, make it 606, okay? It's not big difference, okay? And you need to, since we are working with the alpha is 5%, okay? And this is something like t square root of n minus 1, okay? Then this one is 1 over n, okay? So this one, alpha is equal to 0.5%, and n minus 1 is 686. And what is the critical value? This is pretty close to z, I mean. Such big degrees of freedom. So maybe we can just use 1.96, since it is 5% divided by 2. Okay, so this number is something like this one. So you use this one times this one times this. So what's the number of it? Zero point zero what? Something like 2, right? So 7, 5, okay? All right, so let's use it. These numbers. So this means what? Negative 0.075 up to positive 0.75. So what do we mean? Look at this, those numbers. Those is outside this range. Means the correlation coefficient is too big. Okay, so let's see. Okay, the fourth one. Look at the fourth one. It's 0.098. And if you look at probabilities, it's very small too. So it means that they're outside the range. Reject the null hypothesis of correlation coefficient equal to 0. Okay? You all with me? You all with me? Okay. Then number 4, then keep going. 18. Look at this one. 18, right? This is outside range. And 22. 22, right? And well, whatever. It seems like that. 4th, 18, 22, 25 is a little bit 25, and that's almost, right? Did you see that? So (22) and 25. So we may choose the P and Q, something like this one. And this is the first difference. Look at this one too. You know, this one is PAC is pretty similar, right? 18. Well, this is 18 is a little bit. Then 22. Yeah, it's big too. And 25. Yeah, or something like that. Okay? So by looking at PA and PAC, and we see the outside the range of correlations, and also we decided P and Q, and since we're working with the first difference, so D equal to 1, you know, something like this one. Okay, so we can sort of check in with AMA or MA, ARP, or MAP, and also we can check it, the AR and MA. Okay, to see how that works, how this model works. Well, let's take break for a little while, okay?